So today we're going to be talking about what we had been talking about last year actually is the backbone of modern, let's call it AI, backbone of modern AI, which is the transform model, we're talking about the encoder, BERT architecture, we are talking about the decoder architecture, the GPT sort of thing, like generating text by causal mask attention. And I think to put things into context, like what is missing in order to get us to where we are these days? Like what is contemporary LLM, what they are doing? Is it all the architectures, or is it more to be added to the recipe just to make it work? And this is what we are going to be touching today, and maybe in the next lecture we'll talk about more topics more in depth. But basically, what we need to know these days, since a couple of years now, is the transformer architecture. So we talk about let me just start GPTs, and I mean now when we know the encoder transformer, which is the BERT model. So just for refresher, so the BERT model basically takes a fixed length input sequence of tokens, transform them into indices, and then for each token it creates a sort of like embedding vector in a contextualized embedding vector for each token. And then we can use the CLS token as a special token for classification and stuff like this. So those are BERT. And then we have the decoder transformer, which basically is the same thing, takes an input sequence, do the causal mask self-attention. So basically it just looks into the past in the attention matrix, not into the future, the whole context. And then we use it we use always the last sort of token embeddings to predict the next token. So we're just trying to generate one token after each other, and this is how we generate text. So we have these two things together, and I think we should now look into the origins of that. And this is now a very famous paper called Attention is All You Need, because it showed that it introduced the transform architecture, which is a combination of the encoder and decoder. So usually if you look into introduction to transformers, you will see something like this, which if you are first getting familiar with the transformer architecture, you're saying, oh, it makes no sense. Like it looks too complicated. And as we saw, it's kind of complicated in a way. But what we did is that we split them into two parts. So we are talking about first the encoder part, and on the right hand side is the decoder. And now, since you know already the encoder and decoder, how they work, now you understand that what is the input embedding doing, what is the positional encoding doing, what is this multi-head attention, because there are several heads, and what is n times mean, because we are repeating this sort of layers a couple of times, 12 times, 24 times, whatever. And this is the encoder architecture, and the decoder is again taking some inputs and doing the same thing. And the differences between what makes this a architecture on its own is that if you recall the keys, queries, and values, they were basically taken from the previous layer. From the previous kind of from the input itself, like in encoder and in decoder. But here in the encoder-decoder architecture, in the original transformer, they're coming from one of those. I don't recall exactly whether it's key or query or a value, but they're coming across these two encoder and decoder. So there is some connection between the encoder architecture and the decoder architecture, which makes it somehow entangled together. Anyway, so we're not going to spend that much time on this, but anytime you see this, you should understand what the architecture means. So they're using different kind of namings, but we discussed it already in length. So just highlighting a couple of things, a couple of facts from the Attention is All You Need paper is that exactly. So in the encoder-decoder attention, the queries come from the previous decoder layer, okay, and the memory keys and values come from the output of the encoder. So this is the difference. Like if you recall the simple single head in the single attention layer, you would have Q, K, and V coming from the same input X, basically. So we would multiply it by one matrix to get a query, one matrix to get a value, one matrix to get a key. But the difference here is that only the queries, the Q, are coming from the previous layers, but the key and value are coming from the encoder. So this is how basically the decoder is trying to look into all the context from the encoder. I mean, if you think about it, like what this architecture has been designed to do is machine translation. So the idea here was that you take an input sentence, or input language sentence, encode it, the whole, I mean, what's coming out of the encoder is the whole input representation, and then the decoder is generating token by token, doing the translation, and at any point it wants to look into the whole input to understand the whole context, what should be now translated as an export, basically, or what should be generated as an export. So that's why it's trying to look through the key and value, it's attending to the entire input, so to say. Make sense? I hope so. Okay. So this allows every position in the decoder to attend over all positions in the input sequence. And it mimics the typical encoder-decoder attention mechanism in sequence-to-sequence models. I'm not sure if we talked about this in the RNN sequence in, sequence out, but basically that's where the inspiration comes from. Okay. Then the second part in this transformer is the multi-attention in three different ways. Well, okay, the encoder contains self-attention layers, sure. In a self-attention layer, all of the keys, values, and queries come from the same place. Okay, so this is what we discussed already. In the encoder, the X is going to be projected to query keys and values. And each position in the encoder can attend to all positions in the previous layer of the encoder. So it's looking basically on the entire sequence. And the third thing is in the decoder, we allow each position in the decoder to attend all positions in the decoder up to and including that position. We need to prevent leftward information flow in the decoder, so we cannot look into the future. And this is implemented by masking out all values which are to the right to minus infinity. So I'm basically repeating this from the paper. So because many people refer to this attention is all you need paper as a kind of blueprint for transformers, and some of the details are all of the details now you understand very well because we talk them in this encoder lecture and the decoder lecture. Okay, so if you're ever faced with reading the transformer model paper, attention is all you need, you will understand everything. But as I said, the transformer model was designed for, well, not for everything. So it turned out that this architecture is actually very powerful, but actually it happened before introducing BERT, which BERT solved 14 NLP tasks at once and getting state-of-the-art results. But the original idea of using this encoder-decoder transformer was done for machine translation. So, and since you are familiar with different tasks in NLP, so WMT is a workshop machine translation, and this is sort of like standard benchmark data sets for machine translation. So they train it on, excuse me, one of the standard data sets, WMT 2014, English-German data set consisting 4.5 million sentence pairs. That's not a lot. Actually, it's a very small data set. For this very huge architecture with very many parameters, it's a tiny data set. And they used byte pair encoding with a shared source target vocabulary of 40K tokens. And also similarly for 36, excuse me. Yeah, for English-French was kind of bigger, 36 million data set and 32,000 word piece vocabulary. So this is just putting things into the context. Like what they're trying to solve was machine translation originally. And if you look at some results, is that I'm basically now this is more like sort of like taking things from the paper. So like how research is presented, what they kind of present the results, and if you compare to, you have to if you're doing a new task or new architecture, you have to compare to some state-of-the-art results all the time. And basically, if your architecture shows both numbers, you're kind of better, and your paper gets accepted, and everything, everything is great. And that's what happened here. Is the big, the original transformer model introduced two sizes of the model, base model and big model. I don't recall exactly what the difference is. I mean, the differences were in the number of layers. I think like 12 layers was the base model, so 12 times repeating the transformer layer, and 24 times was the bigger one. So basically doubling the number of parameters in the encoder, and both an encoder and decoder. And as you might see, okay, so what is blue? Okay, it's one of the scoring metrics for what? For machine translation, I would say. Yes. So what is it doing? Any ideas? What is blue scores? What is it comparing? I mean, we're not classifying things, right? I mean, classifier would be accuracy and F1 scores. Well, what is blue doing? How would you evaluate machine translation? Like, you have maybe some references, like a translation. So, and now your model is generating some text. So how do you gonna compare? Yeah.
Talking about metrics, maybe word error rate.
Not really. I mean, word error rate makes sense in some context. For machine translation, there is this blue metric, which is the most famous one, not the best one, but the most widely used as a baseline. So how would you compare this? Like you generate the text and then you have some references. So what you're gonna do?
Check for some sort of similarity between what it produced and what.
Some sort of similarity. So what sort of similarity? What is the easiest thing to compare?
The embeddings?
You don't even need embeddings. What if you just compare the sequences of words? What if you just compare so how do you call a sequence of tokens? Like 2 tokens, 3 tokens? There's a word for that, yeah? No? Like 2 tokens, 3 tokens. You can build a language model around these tokens. N-gram, yes. What is an N-gram? It's a couple of tokens, like N, 3 gram, bigram, 4 gram. So you can take the bigrams or N-grams from your references and see whether they are generated in your output, and compare basically, whether there's an overlap, whether there's some tokens generated in your model, and whether they appeared in the reference as well. So, and this is exactly what blue score is doing. It's comparing it's measuring the overlap of N-grams. So it's like precision-based metric. So you're capturing whether what you generated actually matches some of your references. You can have multiple references. Okay, so check this out. There's another metric called RLHF, which is like recall-oriented score. And if you're in doubt, go back to lecture 1 or 2 where we discuss these things. Okay. So, and these are normalized. So it should be between 0. I mean, now we know it's a precision-based metric. So it should be between like 0 and 1, or 0 and 100%. So all these scores are kind of in percent, sort of in percent. So 100 would be the best, but you don't want to get 100 because it would be like just not too perfect, but you need some sort of variance in the generated text. So blue scores around 40, 50 are kind of considered great. And the transformer model get here like almost state-of-the-art results. I mean, absolutely state-of-the-art results on English German and English French, almost state-of-the-art. And the thing is, like, an improvement by 1 or 2 points in blue score is actually very good. It's very good. It's not like accuracy going from 56 to 57. Yeah, who cares? But blue scores going up by 1 or 2 is kind of considered like a big leap in machine translation. Okay, so this is the original transformer, and I would leave this as it is now. I mean, because this was the origin, but it turned out to be two streams of research and applications, which is like the BERT-based or encoder-based models for text classification, and then one of the contemporary uses is for sentence embeddings. So like sentence BERT and all these things, they are still relevant these days. And the other stream of research is basically the sort of decoder-based models, GPT-ish and everything. Okay? Any questions so far? Good. So here's one thing that seemed little, I would say, very innovative or little radical back in the days. Basically, that you can take every task in NLP, be it classification, regression, text gen, whatever, and turn everything in text to text. So, and one of these, so there's a very cool paper about this by Colin Ruffell and other authors called T5. So T5 was a architecture encoder-decoder model, a little bit, I mean, there were some differences in the architecture from the transformer encoder-decoder, but basically, it's mostly the same type of model. And what they propose is that you would take every text processing problem and turn it into text-to-text problems by taking text as input and producing new text as output. I mean, now from the retrospect, we are used to, GPT or whatever, Gemini. I mean, okay, I'm curious what you're using. Okay, so ChatGPT mostly, raise your hand. Okay, you. Gemini, interesting. Anything else? What is anything else? Perplexity is good, okay. Claude, okay. I see strong bias because I think it's a French company, and I see no, it's not, because is Claude a French model or not? Oh, it's not. Okay, sorry. Where does it come from? Anthropic, yes. I think it's French. At least the name sounds French to me. Like Claude is. Well, anyways, okay. No, whatever. No prejudices or biases. So okay, there's different models. And I forgot why I asked. But anyways, yes. I mean, we're used to this. So basically, whatever you type in, be it coding thing or be it you can ask it to compute the sum of two numbers if you really want to burn some GPUs, like what is 20 plus 20, and give you the answer, which is an integer basically. So underlying everything is text. Like everything are text tokens coming in and text tokens coming out, and sometimes there happen to be numbers or represent numbers. Sometimes they happen to represent something else. So it seems natural. But if you fast forward, if you fast backward, we're talking about a lot of classification things. Like, what is a classification problem? It's a binary task, right? I mean, you have binary classification is a binary task, so it's producing 0 or 1. So all these kind of binary classification of sentiment, it's not generating a number. It's just probability of being 1 or probability of being 0. If you have multi-class classification problem, it's basically producing what? What is a model producing for multi-class classification? It's not 0 or 1, it's something else. How do you encode this problem? Yes? Yeah, but how do you represent the class? Say again? Yeah, exactly. So we continue, yeah? More than one number, yes, so maybe. How do you do multi-class classification?
Typically, we have a distribution over all possible classes.
Yeah, exactly. You take a vector, more than one, and you say like, oh, my class sport is going to be one hot vector, and the position, arbitrary position 2 is going to be 1, and the rest is going to be 0. So you represent the problem as basically producing a vector of ones and zeros. All right, well, 1 and the rest is 0, one hot encoding. So multi-class classification. How do you represent a text generation? Well, it's also like sort of multi-class classification where you produce a vector over a vocabulary, and the most likely word with the highest probability will be the one which kind of outputs. So from that perspective, and there's another task we didn't talk about because it's not typical in NLP, but I think in standard statistics or finance, whatever, it's a regression task. So have you heard of regression task? So what is a regression task doing? Yeah. Linear regression is like linear regression is telling you you have some dots and you want to like that. You know, put the curve, like finding the slope and the bias, like, yeah. So, but what you're trying to predict in there?
The output is different in the sense that we have like continuous values.
Exactly. You want to predict a real value. You want to predict I don't know, like what could be a task of regression. Stock market prediction. You want to know the stock prices of Apple tomorrow because you want to get rich and invest money in that or something like that. You're predicting like a real number. I mean, I don't think actually you would model stock prediction as a regression. Maybe you could. Why not? So you're actually producing a real number. I mean, it could be like with some finite precision, but it's still a number. So here's the thing that you can actually, or what these people are trying to do is take all of them, no matter what it is, what the task is, and everything is text in and text out. So here's an example of input. Translate English to German, that is good. And you put it into the model, and the model is producing the translation, that's good. Okay, good. I mean, we know this. This is like text to text. No, nothing new. But you might do classification, for example, here. Cola, what is this abbreviation of cola? I don't know. Cola sentence. The course is jumping well. And I think this is a classification task of, what was that? Grammaticality or something, or whether whether the sentence is a valid sentence in English or not. You put it into the model, and the model does classification into yes, it's acceptable sentence, or no, it's not acceptable. But it's not giving you like a bit, like 0 or 1, or probability of those. It's telling you actually, yeah, it's not acceptable. Like verbatim answer as a text. It's generating the text as an answer. Okay, sure. And then here's something from, I think this is some entitlement thing. So steps ST, or I think it's some similarity task. Sentence 1, the rhino grazed on the grass. The rhino is grazing in the field. And it should give you some sentence similarity score, which is sort of regression. You want to see a number between, I don't know, like between 0 and 5, how similar these sentences are. And here, you put it into the model, and the model is outputting, yeah, 3.8. But here, it's not a number, it's not a regression task. You're not outputting a number. You're generating a text representing a number. And it's kind of like, wow, will it work? Will it generalize? I mean, now in the retrospect, we see it generalize pretty well. You can do a lot of mathematics, actually, with language models by generating tokens, But thinking about this, like conceptualize this task, it's kind of, new thing, which I believe like help to push the field a little bit. And there's another one, text summarization. You put a text in, and it gives you a summary of this text. I mean, it's again, text to text, it's kind of not surprising. So what is very cool about this is they use just a single model for all of these tasks. There's one underlying model trained on, I don't know what. I mean, we'll have a look into the training. And it's solving multiple tasks at once, which is kind of, not surprising again if you recall the BERT, which was actually pre-trained on some general language modeling task or filling the gap task, and then it would kind of fine-tune on task A or fine-tune on 2 sentences task, fine-tune on classification, stuff like that. So, but here, producing numbers is kind of interesting. So it can, these language models can actually do some regression task. Well, it's kind of interesting. So what was the pre-training? Self-supervised pre-training. So they actually playing around with, is it readable? Yeah, okay, it's kind of small. So they were playing around with plenty different types of self-supervision to see like, oh, what is the best, pre-training task you can train on or pre-train on to give you best results. And there was like, the typical one, prefix language modeling. So thank you for inviting and fill the rest. Me to your party last week. So basically, it's like GPT style model, decoder model, like predict the next tokens. Then the bird style, fill the gap. Thank you, mask me to your party, and shuffling some words randomly. So and you need to reconstruct the original text. There was some other deshuffling, so you shuffle all the words and try to predict the original text, and a couple of other random spans and things like that. And I mean, the paper was kind of extensive because they tried all of these in pre-training this model, the T5 model. And what they were pre-training on, so how do you, again, we're coming back to the question, how do you pre-train your language model? You scrape the internet. And you don't want to scrape the internet, you take some existing scrape of the internet. I mean, unless you have a lot of servers, a lot of bandwidth, patience, and a lot of experience, then go ahead and scrape the internet, but don't do this. And don't do this on the university infrastructure. Anyway, so there's one kind of like, it's an interesting project. So Common Crawl, it started, I think, like around 2010, 12-ish, back in the days. It's a non-profit initiative trying to basically scrape the internet for, I don't know, for anything. So basically, these people, I think it's US-based company. It's not a company, it used to be non-profit. I don't know if they changed something, but they were basically every month, they were scraping the internet. So you can go to, and they were storing this scraped internet as basically raw HTML on Amazon, on AWS, and you can just go and download the internet for you. I mean, if you have enough bandwidth and storage, you can go to Common Crawl, download the internet on your infrastructure and do stuff. And people use it for research in information retrieval, so building search engines and research for that, and it's kind of cool. So every month there's a new fresh snapshot of the internet, lots of overlaps of the same pages, lots of kind of fresh seeds and things like that. And I think they've been doing this since, forever now. So somebody, Common Crawl, crawl the internet for you. It's publicly available archive. And actually it's extracting already the text. So you get HTML if you want, and you get like, stripped HTML content. You basically get just the plain text of these pages. So you can already process it, index it, and stuff like that. So you get 20 terabytes of scraped text data each month. 20 terabytes, it's not bad. It's it's big enough to do some cool stuff. The problem with that is like it's internet. So most of that is really crap, like as text data. So if you train on crap, you get bad models. So what do you need to do with that? How would you solve this problem? You get 20 terabytes of crap data, but there might be something in there. So what do you wanna look for?
Longer, like coherent sentences.
Okay, so you wanna get coherent sentences, longer sentences. How do you do that?
They probably have like proper punctuation and grammar and stuff. Maybe that's something you can identify.
Okay, you can identify somehow proper grammar. Anything else? Any ideas? What else? How to get better data out of the how to get better data out of the internet?
In previous lecture, the example was we had some filters, but they didn't use this as like their baseline. They had like the Reddit filter for.
That's right. Yeah, I mean you can look into the outcoming Reddit. So that was the GPT one, I guess. They took the Reddit links. No, I mean for T5 you get the crawl, and you have no idea where it comes from. But you're up to something. Absolutely, you have to clean it. So so the authors of T5, they created this C4 corpus, colossal clean Common Crawl corpus, which is now compared is 30 terabytes versus not even 1 terabyte of data. So most of as you see, like most of the data was actually useless for any good quality training. But still, you end up with almost 1 terabyte of data, which is higher quality, and actually quality matters. That's a thing. So how do you clean up? Sure. So we retain lines that ended at terminal punctuation mark, so period, exclamation mark. So that's how you get your sentences, for example. You discard all pages with fewer than 5 sentences. Of course, you have some lists, or you're trying to have some lists of bad words, dirty, nasty, obscene, and otherwise bad words. It's a design choice because you're preventing the model from learning bad things. You can do this. Of course, if you see a web page like, oh, you have to enable JavaScript to run this web page, I mean, of course, you want to get rid of those because there's no content. So you get of this. You will be surprised how many lorem ipsum pages are on the internet. Quite a lot. And code, yeah, I mean, back then, they were interested in language model for natural text, like actual language, like spoken language, English, and stuff like that, but not in coding language. Later on, I mean, there's some other models doing so, like doing code. So they get rid of the code and they run some deduplication to get like more variety, so not like repeating sentences over and over. Okay, sounds great. So do you think it's so, now you have a clean data, so just, taking a little bit of perspective. So you have this architecture, this powerful transfer model. You pre-train it on 1 terabyte of data, which is quite a lot. And you're trying all these different tasks and different supervised training and stuff like that. So what do you think actually is the most important thing? Like what matters at most at the end of the day? What makes your model perform best on each of these tasks? Like the best accuracy, the best whatever. What do you think it matters at most?
Seems like the size of the model was a big factor.
Size of the model. Any other ideas? What matters? Yeah.
The amount of data you train on.
The amount of data to train on, size of the model. Any other ideas? The scale matters. You're absolutely right. The bigger, so they tried so many different pre-training stuff, so many different kind of ablation studies, so many blah, blah, blah. And the bitter lesson is you can do so many little tricks. You can do so many different pre-training strategies. You can do so many blah, 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 whatever. The only thing that matters is the bigger the model, the better. The best ingredients for getting, I'm talking about this T5 paper right now. I think we can learn a lot of lessons from this paper, and I think we've seen this, in the other models later on. The scale matters. No matter all these tricks, all these kind of things, if they just add more parameters to the model, it improved the accuracies, scores, F1 scores, and whatever blue scores. The scale matters the most. And I think that's what we see these days, why all these companies are building NVIDIA data centers for more GPUs and things like that, because then you can process more data on much bigger models. So this is I call it bitter lesson. It doesn't say like all these kind of nice tricks, they are useless. I mean, they make sense. They make research interesting. But if you want to really crunch the numbers, get bigger machines, put more data in it, maybe more quality data, and you get better results. Questions? Okay. So let's talk now about the evolution of GPT, because I think it's kind of important. Did we talk about this already? I don't know. Let's see. So the GPT-1 is kind of it was inspired by this by the transformer model. So the transformer model showed up in 2017, and 2018 was the first GPT model. I think we talked about this already. So it was about basically dropping the encoder. So was there was a still paper about this GPT-1 model, and they put away the encoder and used only decoder to on the task of language model for writing Wikipedia pages summarization. So okay, this is interesting. So why do you think actually what benefits are in if you come back to this model, what benefits could be here if you just completely drop the encoder model? What are the benefits? Now you know that scale matters. What are the benefits of dropping the encoder? What do you gain by leaving something out?
We free up the space to just provide the computing for the decoder.
And why? How do you free up the space?
Because we drop all these heads and things of the decoder.
You get rid of all these parameters which you don't have to store anywhere. So you free up the space, which means you can scale up this like, okay, let's make it twice as bigger. And turns out that you don't really need this encoder eventually. I think it was like empirical kind of observation, but you can just scale the architecture of the decoder more, and you get same results or better results than using this encoder-decoder architecture. And by doing so, because you have to encode. Sorry, I just it's not visible anymore. But you have to encode. You have to have almost double the amount of parameters for the encoder and the decoder. All these attention heads, they have to have all these matrices for projecting query key and value, and a couple of times, and all these multi-layer, whatever. And if you just get rid of this, you can scale up one of the architecture, and it works better and faster. So this is the advantage. Yeah.
So does that also hold for machine translation as well?
Exactly, for machine translation, like everything. You don't need the encoder. You just start. How do you do machine translation with decoder-only models, GPT models? Well, you start prompting. You basically do the next word prediction, and you put a first sentence, second sentence, and you train it, basically predicting the next word. That's what you do. So, okay, let me come here. So now we use only decoder that consumes input and produces output, and it's trained as standard language modeling task. So Wikipedia pages a summarization. This is interesting thing. So what is a summarization task, by the way? Naively, how do you build? What is summarization doing? Yeah.
It's sort of condensing information from a text.
Right. It takes a long text and do some condensed information. So why do you think Wikipedia is a good source for this task? What makes Wikipedia special? Any idea? Why Wikipedia would be good for summarization? Yeah.
The whole concept of Wikipedia is kind of summarization of topics.
Yeah, but okay. So how do you? Okay, sure. But how do you create a data set for summarization? How do you create a data set for summarization? That's a question. Yeah, but how exactly? What does it mean? Like, input is text, output is text. Input is something long, and output is something short.
We have the sources that Wikipedia says they're based on.
Ah, okay. So you can crawl the sources of Wikipedia. Okay, maybe there's even easier solution.
Yeah, I was thinking maybe every section has some sort of title, and then what it talks about, the subheading or something.
Yeah. You're up to something there. You can exploit the Wikipedia directly without the external links, or you can even take the first paragraph, which is a summary of the page. Typically, if you look at Wikipedia, the first paragraph is saying like, I don't know, like Julius Gaius Caesar was the emperor, blah 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 blah, and then there's like 100 pages of text, and you can take the 100 pages of text of being your input and the abstract being your summary. It's a very crude proxy task, but it's for free. If you were to do this like really gold standard data, which was a task, for example, for news summarization, you would actually take a news article paragraph and let people write a summary of that. And it's very costly, you get small data and stuff like that. If you take Wikipedia or something which, or there's a famous summarization data set called, I think, CNN Daily News Summarization. Why? I mean, you have the newspaper where the first kind of paragraphs or the abstract is like the summary, and the text, is basically summarizing the main text, so you take it as an input-output kind of thing. So they took Wikipedia. Makes sense. It's cheap and big enough, and multilingual and stuff like that. Okay, so this wasn't even GPT-1 model. This was just the decoder. What is this paper about? Generating Wikipedia. I think it's like one preceding GPT-1. Is it the same authors? Saleh, Lucas Kaiser, Shazir, Google. Okay, there were some same authors. I don't know if it's the same lab. So the GPT-1, and again, the GPT-1 model took the decoder-only transformer from the previous works, and again, pre-trained as language modeling. They fine-tuned with, GPT-1 wasn't really general model for everything. So they had a couple of tasks, and they had a extra final layer for each of the tasks. So you would have basically some, the transformer model, let's say it goes left to right. So this is the transformer. And then you would take task 1 and, fine-tune only this layer for task 1. Then you would have task 2 and just fine-tune this layer while keeping these parameters untouched. So freeze basically, you say, oh, whatever you do in your parameter updates, don't change these parameters. Like freeze the layers of the transformer and just fine-tune sort of the head of for each task. Which makes sense? Okay, cool. So, and they pre-train on the book corpus, 7,000 unique unpublished books. Interesting. So it's kind of really small. It's a really small model. I mean, it's before the T5 model. Okay, so this 2018. And the T5 was 2020-ish, so much bigger model with command curl. But back in the days, 7,000 books, kind of nice. Improving the state of the art on 9 of the 12 data sets we studied. Okay, this was sort of parallel to BERT. So it was for text generation, and I don't know exactly which task they tried, but I think it was like text generation tasks. So 9 of the 12 data tasks improvement. Interesting. Okay, so this was the first one. GPT-2, just bigger GPT-1. The same architecture, decoder model from the transformer, not much improvements in the architecture, making bigger. So just double, basically changing one line of one line of code in your PyTorch, whatever, doubling the number of layers will make you GPT-2 from GPT-1, sort of ish, And then of course the biggest challenge is that, okay, you need now to train it on more data, you need better hardware, so there's lots of, let's say, engineering improvements to make it work. What I did as compared to the training on 7,000 books was, now web scrape, and this is what we talked already last time, yeah, you're right. So they take some high quality, not really bad quality internet data by following some links from Reddit, and 8 million documents. So it's like a factor larger than 8,000. Okay, so 7,000, 8 million, which makes it bigger. 48 decoder layers. Okay, so we're going from 12, 24, 48 onto 1.5 billion parameters. I would call this these days still a large language model. So I don't think you can actually train it on your home GPU. I don't think so. Like 1.5 billion parameters. Yeah, maybe. I don't know. Maybe. Anyone tried? So who is playing around with with GPUs and training models, something like that? Are you trying to play around with that? Yeah. What's the biggest thing you're kind of play around on the custom?
Nowhere near this big.
Nowhere near. Yeah. Okay. So I think you would need like a kind of beefy GPU still these days. Okay. Oh, no, this lecture. Inputs prompting. Okay. So this is the evolution of GPT-2 so far, and then, of course, the next in the line is no surprise, GPT-3. But now, what GPT-3 introduced was kind of very interesting thing that kind of showed up as a miracle. Because so far, what we did is for any output task, there was some training, like fine-tuning, or yeah, again, fine-tuning, or just things like that. You need to train your model. You have your task, you have a pre-trained model. Oh, Bert, you have your pre-trained model and you fine-tune it for your task. So what fine-tuning means, it's changing the parameters of the model, or changing the parameters of just a few layers of the model, but you are doing basically standard backprop training style, or SGD backprop training, backprop style training, excuse me. Which means you need to fit it on the GPU. You need to have a GPU first to run this training, because it's a lot of kind of computation, computing the loss, backprop, updating parameters, computing all these things. So it's very intense. What happened in GPT-3, which was a big model, actually much bigger than GPT-2, is an interesting thing, which is called in-context learning. And so the first paper, GPT-3, first observed that a transformer-based language model trained autoregressively at sufficient scale. So what is autoregressively? You predict the next token all the time, like your self-supervised or autoregress your output. Exhibited in-context learning without any specific effort to the authors to promote it via the training objective or data. So what does it mean? In-context learning is the ability of a model to use inputs at inference time, so no training, inference time, which means you have the model and you type your input and you want to produce some output. And during that inference time, the model adapts its behavior without weight updates in order to solve the task which was not present during training. So this is interesting. You have the model which never saw your task before, and you can show it a task and say, do this, and maybe show a few examples of this task. And the model will adapt itself to your task to solve it. I mean, these days it's kind of obvious, because you say, oh, ChatGPT, write me this, and ChatGPT never saw your essay before. Maybe it did, I don't know. So we're kind of used to this, but it's an interesting property. How does it happen? Like, why in-context? What is in-context learning? So here's an example of that. So standard traditional fine-tuning, which is not used for GPT-3. So fine-tuning is that, what is it? Is it readable? Okay, so I need to zoom in. So you have the model is trained via repeated gradient updates using large corpus of example tasks, of course. So this is the standard thing. For example, you want to do machine translation here. So you show it an example of machine translation, just a decoder model, machine translation. Why not? You're translating phrases like sea otter, and okay, can somebody speak loud French? This loutre de mer. How is that right? Loutre de mer. Thank you very much. So you show these examples, and then after showing the example, of course, what you do, you compute the loss, do the backprop, update the gradients, and and change the parameters of the model. Then you show the next example or batch of example peppermint, which is, for example, and then you do gradient updates, and then you start like plush giraffe, Jesus Christ, giraffe peluche, giraffe peluche. I don't know who came up with these examples, but they're kind of fun. Okay, so after these, sure, you train your model. So here you have some sort of theta, and after that you have theta prime, which are different parameters. And then what you want to do is you prompt it with cheese, and you want to get out, and I know this one is a fromage. Yeah, that's all my French, okay? It's one afternoon in Strasbourg for a Christmas market, because there's a lot of cheese in there. Okay, good. And you get a cheese out, you take a fromage, and then this is how standard kind of fine-tuning works. Sure. And then what I explored for GPT-3, which is a bigger model, is sort of they call it like shot, different shots, like zero shot and few shot and stuff like that. So the shot is like you have just attempts, like zero attempt. And zero shot means that the model predicts the answer given only a natural language description of the task, and there is no gradient updates are performed. This is interesting. What you're saying, the model is translate English to French, the task repetition, and then you say cheese, and you're expecting to say fromage. Okay, good. I mean, we know these, I mean, we are used to this these days because we're using these models, you know, all over the place, but how does it, why does it work? Like, how the heck does it work? You know? So this is zero shot. Basically, you just say like, do the task for me. You give the instruction and then just like do this instruction, which is kind of hard if you think about this. Like if you were the model and you never saw this task before, and it's like somebody saying, oh, you know, translate Chinese to Python. Oh, okay. So you might help the model actually a little bit, or you might have helped GPT-3 by not doing like zero shot, but doing, let's say, one shot, which means you give the task description, so translate English to French, and you get this beautiful example, sea otter, lutter de mer, and then you want to translate. So basically, you show also, you give an example. You don't actually expect the model to learn translation, but you're showing it like what you expect from the model. What should be the input-output kind of pairs look like, and yeah. But you're kind of assuming the model already knows the task. So the model should know already machine translation. You cannot train machine translation by one example, but you show it like, oh, this is what I'm expecting. And of course, like from zero shot to one shot, you get into few shot learning. So still you get a task description, and then you show some of the examples from your, let's say, training data. So your plush giraffe, sea otter, and peppermint. You show the model something what you need to do. And of course, the more examples you're showing, the better chances the model has to understand the task and maybe even learn something. Well, that's why it's called in-context learning. Because the thing is, here you have theta parameters, and here you have theta parameters. So everything happens just during the inference. There is no parameter update. So there's, and you know, some people argue like, oh, it's not actually learning if it's not updating the parameters. And some people say like, well, you show it a task, it didn't know the task before. After you show these examples, it knows the task, so it's learning. So it's a matter of semantics of learning. But nevertheless, the thing is, it's actually much cheaper. Well, depending on the circumstances, but it might be in many cases just cheaper to have one model for all tasks. Because what happens after you finish the task? You start again and you want to do like translate Chinese to Python. And you show, okay, I know Python but no Chinese, but whatever. So you show some examples and then something is produced out of this. So here you're starting with the same set of parameters and show the models how to do this task. You know? So, which makes many things much easier. Why? Well, because you can serve just one model as a provider and let people do the inference and show the task during inference, but you don't need to update the model. You don't need to fine-tune the model for every task you're trying to do. And this is the basic idea of like all these kind of ChatGPT, Gemini, whatever you're using. I mean, they're serving like a base model. There's other things in there like some internal prompt and all these things, of course. But everybody, if you start a session new, most likely you get the parameters of the model don't change from one session to another. What might change is the context, like what is put into the prompt, which you don't see, but that's pretty much it. And the parameters are updated by standard training or fine-tuning maybe once in a while, or maybe not at all, who knows. Okay, questions?
I'm a little confused.
Yeah.
How this exactly works. So when is this applied, or?
So how this works, or why it works, or where is it applied?
So it's like inference time.
Exactly. Yes.
So is it just adding more things to the input?
It's basically prompting. Yeah, exactly. It's basically prompting. Yeah. I mean, there's different words now used for this. I mean, in-context learning was used by GPT-3 people. Some people call it prompting, prompt engineering. There's different names for the same thing. Like you just put your inputs to the model, and either you show examples, right, or instructions, or like for zero shot, it might be like instructions. So you just say, this is the instruction to the model, and then you show the actual task, or prompting, prompt engineering. But zero shot, few shot learning is interesting because you can actually show you can compare in context learning just the inference time without any updates of the model with actual fine tuning, because you can take these examples and fine tune on them, and that's what I did, like comparing fine tuning with just in context learning. And let me just, okay, so here's a small sidestep on pre-training data of GPT-3. Okay, so now what you have is 400 billion tokens from Command Crawl. Okay, so they started using Command Crawl. There's still some books, some small books, million. Wikipedia is the smallest one, of course. So most of the text for GPT-3 comes from the internet. So you start basically crawling the data, and the more data, the merrier. So it's kind of clear. But here's the interesting comparison. So if you show, like, this is awesome. So on the X side, this is the size of the model, number of parameters in billions. So GPT-3, 175 billion parameters. It's a big model. It's still large language model. So they started with smaller ones, and then you can compare performance on. I mean, this is one task. Okay, so trivia, question answering, some sort of question answering task, whatever. And you can compare not only zero shot, one shot, and few shot. Well, few is 64, or whatever few means, it's up to you to decide. But zero shot is basically just showing the instruction. And of course, they were comparing to just fine-tuned state-of-the-art model. So some sort of, I don't know what was the state-of-the-art models back then, but basically you take the training data and you fine-tune your model. And what you see here is that just a one-shot learning actually, with the biggest model, matches the performance of fine-tuning some models. So this is interesting. And with showing more examples, you actually perform better than state-of-the-art fine-tuned models. So the bigger the model and the more examples you show in context learning, the better results. Scale matters. There's some other results here for superglue. Okay. Superglue is some sort of a glue is general language understanding evaluation, and superglue is a bunch of data sets together. And again, random guessing is somewhere here, and zero shot, one shot, few shot. So few here equals to 32. And comparing to fine-tuned BERT, large model, with few shot learning, you're surpassing with the biggest model. You're surpassing the fine-tune. I mean, on this task they didn't measure the performance of the state-of-the-art fine-tune model, but still, it's really interesting. It's really interesting that this thing can actually, without the parameter update, can learn the task. And you might be asking why. What the heck is in-context learning? And that's actually a very interesting question to ask, because who knows? I mean, it's an active research. Okay, let me just skip this. GPT-3 large models generate plausible new articles. Of course, yeah, I mean, 6 years ago, it was a big news. These days, we're kind of used to this. And, to be honest, like most of the websites I'm searching these days, like, no, it's GPT generated, of course. I mean, it looks so bad. I mean, not bad, but it's like no person wrote this thing. Yeah, we're living in an interesting world. So let me skip this. But why does in-context learning work, actually? What does it mean? And it's an active area of research. You'd be actually surprised. Like, so one of the naive ideas could be, you're solving a new task which you never saw before. Yeah, is it true that you never saw this task before? Because if you scrape the whole internet, what are the chances you scrape also the data set you're actually testing on? It depends. It depends. And there are very cool research papers showing that over time, GPT-3 or GPT-4, I don't know, one of these models, got better at certain tasks. Why is it so? How can GPT get better on a task? I mean, on evaluation task. How is it possible? It's impossible. It means the task has been presented to GPT during inference time, and of course, what OpenAI is doing, they're collecting all the data which you prompt in, and every couple of weeks or so, they update the model with all the new data, which means all your inputs are actually ingested to the weights. I mean, the model is fine-tuned on your data, which means it already saw your test data. So if you test something now on GPT-4, whatever, 5, and use the same test data set 1 month later, you have no guarantees that actually you're testing on fresh data. So it's, how's it called? I think the term is, I forgot its term for that. Not polluting the data. A data leakage or like, yeah, I think like you're leaking the test data basically to the model. So it's sort of a cheating. But it still doesn't explain like why it works on all the tasks. So there is something in the models that actually triggers the learning. And here's one example, what makes in-context learning work. We show that ground-truth demonstrations are not required. So this is one example. Randomly replacing labels in the demonstration barely hurts performance on a range of classification and multiple choices tasks. Instead, we find that other aspects of the demonstrations are the key drivers for end-task performance, including the fact they provide a few examples of the label space, the distribution of the input text, and the overall format of the sequence. So this is interesting. What they're showing in this paper is this 2022 NLP paper that it's just enough to show the model what you're expecting as the output format, and maybe what are the labels in labels if you do classification, like you're classifying into topics or whatever, and it already triggers the model to sort of like think around these like to shift the distribution of the generation into these areas. Still sounds a little bit obscure and abstract. There's other papers. We explain language models as meta-optimizers and understand in-context learning as implicit fine-tuning, which is interesting. Theoretically, we figure out that transformer attention has a dual form of gradient descent. So if you're interested in something very cool, as a research, go into explaining why in-context learning actually works from a theory point of view, or I mean, it's literally an active area of research because we don't really understand why it works, not how it works. I mean, we know how it works. But why actually is in-context learning works? And there's a couple of other papers showing that in-context learning can only happen with the scale of the model. So the bigger the model, from some point, what actually happens is that the capabilities, so they call it like emerging abilities. So emerging capabilities of the language models, and they happen only from a certain scale. So small models, they cannot do in-context learning for some reason. Just if you have big enough model, they start to have these capabilities of in-context learning. And this is what makes this big model kind of really shine, is this ability to learn just from prompting. This is kind of very interesting. Anyway, so in-context learning takeaways. Even if your weights of your language model or the parameters are unchanged, some form of learning actually takes place. Something is happening in there, just in the inference time. If you show a couple of examples, show what to do, there is something. And if you show more examples, what you want to do, then obviously you get better results. I think from your experience, if you do I don't know what you're using your language models for. I hope not for, I don't know, writing essays or homeworks. But have you tried to show a few examples what you want to know, what you're interested in, and it works better? I don't know. I mean, did you? Okay.
Yeah. Project, we basically had to build more or less a GPT wrapper. But
oh, okay. That's interesting. So what did you do in there?
It's creating process models.
Okay. For what?
For business processes.
Ah, okay.
And then you give a predefined structure of how you want these process models to look like.
Okay.
And then kind of works.
Yeah, so you're showing examples in context and then it kind of works. So basically you're drafting your prompt in a way that it knows the task in like that.
Yeah.
Okay, yeah, cool. Makes sense. Because if you just say like, do me process models,
Doesn't really work.
doesn't really work. Okay, makes sense because it's kind of weird domain. Okay, cool. All right. But, you know, the takeaways is that it has profound practical impact on LMs, language models, because you don't have access to the model weights. By the way, I'm pretty sure that, you know, well, the architecture of transformers is kind of known, so there's no secrets in there. What makes these companies, you know, OpenAI and others, Claude, Anthropic, what makes their assets is actually the train models. So you will never see their training data. I mean, back in, you know, GPT-1, they showed like, oh, we have, you know, Wikipedia and these books. GPT-2, like, yeah, and web crawl, but you cannot really access it. And then GPT-3, okay, we don't say anything about training data. So you have no access to the training data. And of course, you have no access to the weights of the model because this is what matters. So it used to be possible, you know, you could actually steal you can steal a model in a way. If you have infinite access to the API and just the output weights, just the output of your prompts, you can start, you know, prompting the model in a way that kind of it can reveal the weights of the model. So you can sort of steal the weights. But of course, there's some restrictions in place through API access, and you know it's kind of costly. So you cannot steal the model. You cannot steal GPT-5. Yeah.
Isn't that what they're using DeepSeek of all the time?
Maybe. I don't know what DeepSeek did. I mean, DeepSeek is as secret as everybody else. They're saying like, oh, we train it, you know, with fewer GPUs. But I didn't study this thing in detail. I don't know. Maybe they were stealing the model. You can, I mean, theoretically and practically, you can steal the model weights, like mimic the model weights. You can use it as a teacher, like a model distillation thing. So you have a bigger model, which is a teacher, and you teach a smaller model and things like that. Yeah, you can do this. But still, like what is in-context learning enabled you is to provide just an endpoint, like an input text and output text through whatever API or just, you know, input fields, and everything can run somewhere else, and you never see the weights of the model, which is much different to like a BERT. If you want to do classification with BERT, you need to download it and fine tune it, and you have, you know, all these kind of infrastructure problems. So this is a big thing. Okay, questions? So let's move to, let's say, a collection of topics, which are a bunch of things I put together here. But I think, like for the next lectures, I'm going to focus on some aspects which might be like more practical oriented for, you know, what can be done in LLM, and maybe some little bit of research. I mean, still open. So I'm thinking of like retrieve augmented generation, which is a thing like everybody's using these days. So how this works, maybe could be interesting. Okay. Maybe some security aspects like privacy or stealing data or some attacks. I don't know. I'm not decided yet. I have to figure out. But here's because the thing is like this is an active area of research. So some techniques are now obsolete already, and some will come, you know, next month, and might change everything or not. So it's kind of really hard to navigate through this landscape for lectures. So it's gonna be more like, you know, oh, here's the paper, here's another paper, and they did that and that and that. So I hope you'll enjoy it. Because this is very rapidly changing fields, to be honest, you know. So, Llama 2. So this is another meta model. Llama 2. What is this? What is now out? What is out? Llama 3 is out, I guess. I don't know. I think Llama 3.7 is like the latest model from Meta. So Llama 2 is that they started with basically like being models more helpful, so to say. Because if you just train a language model, just a plain vanilla language model, and you prompt it, it will continue the prompt, or it will just generate, you know, the continuation of the text. Because it doesn't know, so to say, what you're asking for, typically. You have to sort of either give the instruction and the example, as in, you know, one-shot in-context learning, or fine-tune the model, or instruct the model or fine-tune with instructions that the model is kind of actually producing the output you want as the user. You know, like it's not a base language model. It's like sort of a tool for you to use. And with Llama 2, they started collecting results where they were annotating helpfulness and also safety and some other features for supervised fine-tuning of the model, where the annotator has written both the prompt and an answer. So now we're in the, we have the pre-trained model, it's 2023. You have the pre-trained large language model, and you want to make it helpful and safe and all these things that we are kind of, used to now these days. And they let people write the poem to help me remember. Jesus, I wouldn't like, can you imagine you're an annotator, by Meta, and you're writing this prompt, write a poem to help me remember the first 10 elements on the periodic table, giving each element its own line. And then you have to write a poem actually and being paid like 50 cents for an hour or something like that. I don't know. I mean, maybe they were paying more. So this is lots of very expensive data. Or I want you to roast me. I want you to make it particularly brutal, swearing at me. And here, of course, I'm sorry, but I can comply with that respect, using vulgar language, blah, blah, blah. So you're kind of, you want to try to censor the model, not to output things that somebody's don't want to see. And you want to make it, helpful here and safe here. Okay, so they had 27,000 of these pairs, which is quite a lot. I think it was very expensive actually to let people write these, prompt and response. But several thousand examples, high quality supervised fine-tuning data, as in the previous table. And what I found that these annotations were enough to achieve high quality results. So this is turning the model into being actually useful for tasks you want it. So you ask a prompt like, this is basically just instruction. So some other term for this supervised fine-tuning is also, I think, like instruction tuning. So you give an instruction and the response, and you fine-tune the model to kind of understand different aspects of helpfulness or safety. So you take a couple of thousands or tens of thousands of the data, and your model is giving you better results. I don't actually remember what the tasks were. How they evaluated that these are high quality. I don't remember that, but it's absolutely in the paper. Okay, and there's another thing, because this is very costly. Like, you don't want to write people, 20,000, 30,000 poems on a periodic table of elements or things like that. It's just like, it's pretty scary. So what you want to do is that another paradigm is called reinforcement learning with human feedback, where you want to utilize the model. I mean, the model is already able to generate something, but you can select human preferences, like whether do you like the output A better than output B. And I think do you see it like once in a while that the model is asking you like, do you like this better than the other? Yeah. So you're the annotator for not only you're providing the input data, but you're also annotating data for these companies, saying like, oh, I like this better than the other. Is it a good thing or bad thing? It depends. I mean, you're using the model for free, so there is no free lunch. I'm sorry, unless you pay, but still you have to annotate the data. I don't know. Anyway, so you say the human annotators select which of the two model outputs they prefer. This human feedback is subsequently used to train a reward model. Oh, okay. Which learns patterns in the preferences of the human annotators and can automate preference decisions. So what you're doing is that you have this big model, Llama, GPT, something like that, and then you have another model which is basically only used for the reward, which is seeing the input and the output. The model is saying, oh, it's basically a ranker or sort of like preference learner saying, oh, this output is better than the other. So it steers the model. It gives another signal to the model. It could be used for fine-tuning the model such that it's more helpful or kind of corresponds to human preferences. And it's much cheaper to have this model for automatically annotating your data than having people like write it all the time, all these pairs for supervised fine-tuning, or just let people click all the time. I mean, you use this for creating a model in the loop, and then you use it in the loop to improve your the model's outputs. Okay, so here's the procedure. Excuse me. Here's the procedure as that we ask annotators to first write a prompt, then choose between two sampled models' responses based on some provided criteria, helpfulness, safety, and things like that. In order to maximize the diversity, the two responses to a given prompt are sampled from two different model variants. Okay, interesting. And varying the temperature hyperparameters. So what is the temperature?
It's how deterministic the output of the model is, like the probabilities.
Okay, probabilities, yeah, we're somewhere. What exactly?
I mean, it means how uniform or non-uniform the
Okay.
probabilities are.
Yeah, in a way. I mean, it's reweighting the softmax over the vocabulary generation in a way. So the higher the temperature, the more creative, uniform. The more random, the more uniform the distribution is. We had this on the exercise last week, not last week, like before Christmas. Okay, so you can, the creative is like, yeah, the more variance, and there's this nucleo sampling, top P sampling, and things like that. Anyways, you have, in addition to giving participants a forced choice, we also ask annotators to label the degree to which they prefer their chosen response over the alternative, either their choice is significantly better, and so you're basically collecting the data, and you use this to train this reward model. I hope it's readable. Let me just zoom in. So we have a prompt. Explain the moon. Oh, it's really small. I'm really sorry, but here it's saying that explain the moon landing. Excuse me. Explain the moon landing to a 6 years old. Then there's this output, and you. Oh, excuse me. I need to. No, this is the alt, like this is the supervised training. But here, the reward model, so you generate different answers to the prompt, and the labelers basically rank these answers saying, oh, D is better than C and it's better than A, and it's kind of equal. And you use this for training the reinforced, basically the reward model. So the reward model, if it sees 4 answers, it can rank them by whatever, some criteria, helpfulness, and things like that. So one answer is better than the other. And which means this model is then used for, in the next iteration where you have a prompt, write a story about frogs, then you generate the output once upon a time, and then the reward model is giving the output some reward weight, and use this for this preference policy optimization thing. So it's basically like something from reinforcement learning, like there's a loop in there, giving a final feedback on how helpful this answer was, giving this reward model, which was previously human annotated. So, okay, this is a conclusion to this potpourri of things of how do we get from. I mean, there's more obviously. There's like in the last 2 years, DeepSeek. So what makes it different from GPT is there's some other bunch of tricks like this reasoning. So you generate some intermediate outputs, and use it as reason. You don't show it to the user, but it's like pages of text where the model kind of thinks. There's other chain of thoughts, like you say, basically think step by step, and the model is kind of prompted to kind of, think differently and things like that. So I will try to put it into some, concise lectures on some of these topics to explore more in detail. So it might not be all these 4 lectures, but let's see. Any questions? Okay, thank you, and I'll see you later today.